All right, we are now on the classification approaches roadshow. First and foremost, we won't talk about accuracy until the very end. We'll contrast the models just like we did in the previous lab after we fit them all. Um, the first thing that we will be looking at is a k-neighbors classifier. So k-neighbors classifiers are very good when class members are close to each other in multidimensional space. So in this particular example, the fact that all these red dots are close to each other indicates that k-neighbors, might be a reasonable approach. That said, in cases where you have lots of red dots like this one, these red dots over here that are surrounded by lots of blue dots, these will be misclassified in the k-neighbors classifiers. And again, we will go over the nuance of these models in more detail in class. This is more about the technical implementation. So fitting these models is very straightforward. It is from sklearn. All right, and that's all it takes. So we've now fit a model. We've gone in, we imported the k-neighbors classifier. We set nearest neighbors to 10. So essentially what this will do is it's going to go into every single dot. So it'll go into this dot, for example, right here. And it will say, what are the 10 closest dots to it? And it will say, oh, they're all blue, so we're going to guess this point is blue. And that's really the heart of these k-neighbors classifiers. We want to actually visualize, though, how this worked. In the regression case, we were looking at those continuous variables to try to get an idea of how well our models were working. Here we want to do a little bit better. We actually want to see in multidimensional space where the classifiers predicting things are red and where the classifiers predicting things are blue. So to do that, we'll take just a few lines of code, and I'm going to write these out, and then I'll walk you through exactly how to interpret them. All right, so here we have it. This is the ultimate figure that we're attempting to output, which is exactly what it looks like. Areas in blue are where the k-nearest neighbor classifier would predict that the dots are blue, and then areas in red are the areas where it would predict it's red. One nice thing about this particular notebook within Jupyter is we can zoom in to different areas. So I'm going to zoom in to the lower left here. And this gives you an example of kind of exactly what's going on, where all of these red dots are. These are areas where there was not high foot traffic. There tend to be low convolutional neural network values as well as low image brightness. So these are areas the model would prescribe a very high probability all of these points are not busy. You can see if you look in the lower left-hand corner, there are cases where there are blue dots. There were minutes that are still busy. So that means there are a few minutes that have low image brightness and low convolutional neural network values, and we would get these minutes wrong with this model. There is confusion there. So these models are trying to avoid that. Similarly, out here, you'll see there are some red dots in the area the model would predict as blue at times that are busy. So this is the results of this particular k-nearest neighbor classifier. Now let's scroll up to the code and actually see what we just did. How did we do this? So to fit the model, all we had to do was this. This created our predictive model. So there's, all of this code is really to create this particular figure. What we do is we effectively create a grid that overlays this entire square. So you can imagine a big square grid, and for every single one of those grid cells, we apply the model. So we actually do a prediction for each grid cell. So you can imagine there's this grid cell right here that's this big square. Right in the middle of this grid cell, we would have a point where the convolutional neural net value is 150, and right here, the 150, and then we would have a 2.5 down here for image brightness. So 2.5 and 150, we can put those into our model and see what the model would estimate. And if the model estimates that that value is high foot traffic, then we can color this square in as blue. And so that's all we're doing, is we're actually going behind the scenes, and we are literally behind the dots, and we're just estimating for every region of space what our value would be. So we're going to fit, in our case, it's around 100,000 models to figure out what every single pixel should be colored as. So to do that, first what we do is we create, and that's what all of this is doing, we create our grid. So first we create the grid with our x1 and x2, which is the equivalent of our convolutional neural net values and our image brightness values. You can see the ranges here from 0 to 30 and 0 to 180. So here we have 0 to 180 and 0 to 25 in this case. And then this value here is the increments. So in the x dimension, every 5, we're putting a new value. in the y dimension, it's every 10. We're putting a new value. So this defines the size of your grid. Don't worry too much about this. You can type in XX on your console to see exactly what this is doing, but this is just a programmatic operation we have to do to get it into the shape we need. This is where we're actually going to scale our X variables. So because we scaled our underlying raw data up here, we need to scale it in the same way. So we're just basically applying the scalar to our grid. Here is where we're actually doing the predicted probability. So for each grid cell, we're actually running the model, fitting the model. This, again, is just a programmatic element we need to get into the shape we need. You can type in Z in your console to see exactly what this is doing. And then all the rest of this is nearly the same as what we did up here. We're just plotting out those points. The only thing that's new is this. We are creating a contour map where we're defining the X and Y coordinates of our grid, the Z, which is our predicted outcome, and then a color map of red to blue. So the reason that it's going from red to blue is because we're defining that here. So this is really the only new line in the visualization. Just like we did last week, what we'll actually do is take this and convert it over into a function. So I'm going to do that right now. All right, and there you go. So just like a nice little cooking show, all I've done is I've taken the information up here and I've copied it down into this function. The only thing that is important for you to be aware of in the function, because almost everything is identical, is one, we now specify the model in the function. So on this line where we predict what Z is, up here, when we did Z, it was Z equals nearest neighbor dot predict. Now it's Z equals model dot predict, where model is defined in the function. So you'll see when we call this function down here, viz classifier, we have nearest neighbor. So this is the actual model that then is going to go right here. The other thing to be aware of is this. We have the first time we're using a global variable, in this case the scaling model. The reason for this is the scaling model we want to use lives outside of this function. That is, we defined our scaling model up here. So the scaling model exists somewhere that is not inside of the function. Because we defined the scaling model up here, we need to tell the function to look for the scaling model in a different scope. And so this just tells it to look at that scaling model we defined in another cell. There are lots of different ways we could do this. We could even include it up here as something we pass into the model, but this is the most straightforward. This is not great coding practice, but it will get the job done. So I'm going to go ahead and run this, and this should give us the exact same thing we saw a moment ago. And there we go. You'll see I also added a title here to avoid any confusion. So the plot.title. So this is the exact same thing we were just looking at right here, but now we're calling it from a function. So we'll be able to use that for all of the machine learning models throughout this lab. The next thing that we'll want to do is we're going to go in and we're going to do a support vector machine. So support vector machines are very, very good for cases that can be described by straight lines. Support vector machines are essentially going to be identifying straight cuts through your data that can define, everything on one side of the line is a red dot, everything on the other side of the line is a blue dot. This is the sklearn we're going to import from support vector machines, and then this is a support vector classifier is what SVC stands for. We'll go ahead and fit this model. It's just one line like before. There we go. So now we have our fit model, and then all we have to do now is put our fit model into this visualization function that we had before. So we'll go ahead and put in the viz classifier and run this. And voila, so here is the support vector machine. And you can see that there's a clear straight line. So let's go ahead and zoom in. I'm going to zoom into this lower left-hand quadrant. And you can see here, there's a line that is being used to subdivide that's roughly right here. As things get farther away from the line in this direction, we're increasingly certain that they're red. As we get farther away in this direction, we're increasingly certain that they're blue. And you can see kind of throughout this graph where this, these lines are effectively being represented. So the next thing is sometimes these, every single one of these splits that you see are based on straight lines. Sometimes patterns that we see are not actually best represented by straight lines. Sometimes patterns are represented better by circles. So the next thing we're going to look at is a derivation of support vector machines that allow you to define circles, and these are called kernel models. It's not just circles, but all sorts of different shapes. So here I'm going to go ahead and import the same thing as we did before. So this is still considered a support vector machine. It's still a support vector classifier. And all we're going to do here is we're going to change a few parameters. So you'll see in this call, we had kernel equals linear, and then c equals 0.25. Don't worry too much about these things. Down here, what we're going to do is we're going to explicitly define a few different parameters that allow us to build a kernel fit. These parameters there are a lot of them. There's a lot of nuance in how you describe them, and we will talk more about those in lecture. Just like we did before, we'll then do the viz classifier, and we'll see what this looks like. All right, and here we go. So this is the kernel SVM, and this is the linear SVM. So let's zoom in around 5 just to show you what the difference looks like. So this is the linear SVM, and you see 5 is right in the middle of our image. And then let's go down here, and we'll zoom into 5 as well. And this is the kernel SVM. So you can see in the kernel SVM case, the actual kind of model is breaking up the space in much more complex ways, right? In the linear SVM, we just kind of have one line. It's roughly in the middle. As you get farther away from that split, you have more probability of classification. Here we have a much more complex pattern. The red is kind of located farther down, and the way that the space is split up is just more complex because the kernel models allow for more complex ways of splitting up the space than just these straight lines. The kernel is no longer enforced to be a linear. The next thing we're going to talk about is a decision tree classifier. So decision tree classifiers are very, very similar to the regression trees that we used in the last lab. This is our classification tree results. And the classification tree, if you'll recall, is based on splits in your data. So, you can see very clearly it's saying anything with image brightness that is less than about let's call it about 2, and with a convolutional neural network value of greater than 20, any case right here, all of those are going to be classified as blue. So it's blocked out that space. Anything that is greater than about 20 for CNN and about 2 for image brightness, anything over here, there's a different probability that it is going to be blue, but it's still a very high probability. We can see if we zoom in a little bit farther on this particular chart, you'll see these breaks, right? These are very hard breaks where the model is simply saying anything less than a given value is going to be classified as either red or blue. We can visualize this in the tree just like we did before. So I'm going to copy and paste some code from the last lab that we did, and this will be nearly identical to what we saw before. And I'll go ahead and put this underneath our visualization. So the only things to be aware of here is now we have class names, and we have the low foot and high foot traffic for our graph. Everything else here is the same as the last lab. So you can go look at the last lab for kind of a breakdown. If you get an error about GraphViz, you can also refer to the last lab of how to fix that. All right, so we'll go ahead and run this, and there we go. So this is the tree that is representative of this particular scatter plot. So you can see, let's see if we can actually find a split here that would make sense. So let's look at this. So we have a clear split here of image brightness of less than or equal to negative 0.235. So this is this would be below the mean of image brightness because this is in the this is in the units of our standardized data, not our real data. So we're probably talking somewhere pretty low. So probably somewhere like right around 5 in the real units. So if we zoom in on that, let's see if we can actually see there's a hard split somewhere around here. So here's 5. It actually might be a little bit smaller, right? So we might be talking somewhere right about here where we're going to start to see a hard split in where the model will classify things as having been busy versus not busy. So again, this is just a visual representation of this flowchart. It's a visual representation of if you had a new observation at this point, how would you classify it? All right, so the next one that we're going to look at is a random forest classifier. So random forest classifiers are very, very similar to decision trees. The difference being that a random forest classifier is going to fit thousands of trees as opposed to one of these trees and provide us with the kind of average results from all of those different trees. All right, so as you'll see, this is taking a little bit longer to run. Now, in this case, we can't actually get this tree. So you see the tree from our single tree. Because we just literally fit 1,000 of these trees, we can't get that result. What we can do, though, is we can do the visualization. So just like we did with every other one, we can do our viz classifier to see for a given unit what the average estimate would be. You can imagine this essentially as saying, okay, within one tree, we're going to estimate, we're going to follow this one tree. We can also build 1,000 of these trees, follow all of the trees, and report the average probability that a unit of observation belongs to a given class. And so this is what that output looks like from our random forests. Right, now we're going to fit one more classifier, and this one will be a neural network. All right, and there we go. So this is the neural network output from the same thing. And we can see, all of these algorithms are picking up on fairly similar patterns. In the case of the neural network, we have, let's zoom in again on this region down here. And so you can see, very similar splits in terms of the overall estimates that we would be providing for the neural networks. All of these algorithms are fairly capable of identifying the difference between busy and not busy cases. So what we're going to do in the next video is talk a little bit about how we can compare these in terms of their accuracy and select one to do our near real-time predictions.